from 2 to 3, 3 to 2, 2 to 4, 4 to 2, 3 to 5, 5 to 2. And all these things are going on at the same time. We just happen to be able to see with our eyes that one, and that one, and that one, and 6 to 2 as well. We just happen to be able to see that with our eyes. But as I said the other evening, if you start shining light through hydrogen atoms, if the light has a broad spectrum of all the photons in it, photon energies that match the energy jumps will be absorbed by electrons. For example, an electron from hydrogen atoms right here can absorb a photon that will take it here, a photon will take it there, a photon will take it there, a photon will take it there. You can see the absorption spectrum. And it becomes like a finger. The same as the emission spectrum is a finger as well. And so in this way, astronomers can see, looking at the light coming from stars, what kind of elements are in there. In this way, helium, for example, is detected in the sun. So the other form, delta E equals the energy of photons, which are being emitted or absorbed. The other way of writing the energy of the photon is not to use its wavelength, but use its frequency, h times nu. So h times nu equals 2.180 times 10 to the negative 18 of a joule into 1 over n1 squared minus 1 over n2 squared. Or if we divide each side by h, we get what's called the frequency version. 2.180 times 10 to the negative 18 of a joule over 6.626 10 to the negative 34 joules seconds. 1 over n1 squared minus 1 over n2 squared. And this ratio here, the joules cancel, and we get 3.290 times 10 to the 15th seconds to the minus 1. Or hertz. And this is the frequency form. Of Rydberg's equation. So you would use this form if somebody gives you, instead of the wavelength of the light, somebody gives you the frequency of the light. And you can use this version.
So what is that number, the 6.1?
That's Planck's constant.
But what is it,
626 times 10 to the negative 34 joules seconds. Now, if you plug it in, this thing, you'll get 3.29 times 10 to the 15. So, let's do a couple of wee exercises now, using some of the different spectral series, emission and absorption. Let's see if we can find that. Okay, well, so here is a typical little exercise now, absorption and emission exercise. So for example, a hydrogen atom in its ground state, we start off with the electron being in its ground state, okay? Doesn't have to be. You can have the electron in any one of these other states to begin with. It can be just temporarily in there. Then you hit it with another photon and bump it up somewhere else. So we'll start with its ground state. That means N1 equals 1 it absorbs a photon wavelength. I'll use the wavelength form just for now. What's its wavelength? Where is it going to? Well, about 93.07. 93.07 nanometers. It then emits a photon. Let's see, yeah, we'll throw in a frequency thing later, just to make sure that we can. So let's say it goes from, 1,005 nanometers. 1005 nanometers. So we ask ourselves, to which level was the electron in the absorption and to which level did it return after during the or in the emission process. While it was undergoing its emission, where did it end up? Okay. And all of these is use the formula. So we'll use this to say we've got the two wavelengths, and of course keep in mind we could have given you two frequencies, or we could have given you one wavelength and one frequency, so you might want to use one or other of these versions of the equation. Obviously you can always just use the same one. If you're given a frequency, you can always turn it into a wavelength by dividing it into the speed of light. And then off you go. So here we'll go absorption. We have 1 over 93.07, I think it was. It is 1 over 91.1 times 1 over 1 squared minus 1 over n2 squared. I'm going to keep the label n2. If you want to just call it n, that's fine. You know, so cross multiplying 91.1 nanometers over 93.07 nanometers. Let's see, what's that? .9788. 9788. The next digit's a 3. So this is 1 minus 1 over n2 squared. One is exactly 1 on the right. It has as many decimal place zeros as we want. We'll only need 4. So we bring this guy across and subtract it. It'll be 9788 minus 1, so it'll be minus 0.0212 is minus 1 over n2 squared. 2 minuses is good news, 2 pluses is good news, a plus and a minus is bad news. 0.0212 is, .978 minus 47.2 equals n2 squared. So n2 is the square root of 47.2, the square root of 47.2, which is 6.87. Well, that's going to be our integer 7. Our n2 has to be an integer. So what we had was our electron started out in level n1 equals 1, and now it ends up in n2 equals 7 by absorbing that photon, 93.07 nanometers. There's an exercise in the book, in this worksheet there, I think it's the first one, which has a wee thing about frequencies of light that are emitted by some gallium water. Actually make an energy level diagram. It's a nice wee exercise. I don't want to take a look at it. the absorption, the emission process, where does it go after it emits that whatever it is, 1,000 nanometer photon? So, emission. Keep in mind that we now know the higher level one and two. We want to know the lower value for the quantum number n1. This guy is going to drop from here to some other level and emit a photon of wavelength 1,005 nanometers. So our wavelength, 1 over 1,005 nanometers, is 1 over 91.1 nanometers, 1 over n1 squared, n1 is a guy we don't know, minus 1 over 7 squared. We know what n2 is. n2 is 7. Remember, n2 refers to the integer number referencing the higher energy or higher energy state. n1 references the lower energy state. So if we take our 91.1 nanometers and divide by 1,005 nanometers, we get 1,005, we get 0.090646. 0.0906, I'm going to call it 65. Just write it down for 4 digits. And that equals, of course, 1 over n1 squared minus 1 over 49. Which is 1 over n1 squared minus 0.020408. So I'm going to match the decimal digits here. So I'm going to run this thing off of 4 significant digits anyway. I'm going to match out those 4 decimal place digits in that way. So 0.09065. I'm going to bring this guy across, okay? And 0.065 plus 0.00041. Yeah, 0.1191. 11106, but 06 is what we have. We have 5 decimal place digits. 111. You can see that 111. That's 1 over 9, right? So that's 1 over n1 squared. So n1 squared is reciprocal of that guy, which is 9.004. n1 is obviously 3. So, here's a little energy diagram showing what happened in the process. The electron started out light in its ground state. This means this is level number 1. Lower quantum number n1 is value 1. And absorbed this 93.07 nanometer photon, which